Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel, and today's topic of discussion is the ammeter. Our objective today is to take a quick look at the ammeter function of the digital multimeter. We'll use the function, leads, range, and placement checklist for ammeters and discuss the direction of induced conventional current for simple DC circuits. If you'll recall, during the ohm meter and voltmeter lectures, both available at the Big Bad Tech channel, I introduced both the ohm meter and voltmeter functions of the DMM. If you haven't checked these lectures out yet, I'd recommend doing so now because we'll be following a similar format using the same hardware to discuss the ammeter aspect of the DMM. The DMM is again a single meter that has multiple, hence the term multi-mode settings. DMMs can be used to measure both DC and AC voltage, DC and AC current, resistance, capacitance, forward bias voltage of a diode, frequency, and much more. Today we're only going to briefly look at the ammeter function of a DMM, where an ammeter is a device used to measure current through a circuit in units of amps. This is the briefest of brief summaries about ammeters and serves only as a springboard for later discussions. Stay tuned for application of ammeters and other common lab instrumentation in this playlist for experimental verification of Ohm's law and other circuit properties. The same disclaimers apply for the ammeter orientation as it did for the ohm meter and voltmeter lectures. I have no idea which DMM you're going to be using during the course of your employment, school, independent study, or hobby work. It is for this reason that I'll employ 3 different DMMs in ammeter mode during the course of this lecture. They are the Fluke 87, the BK Precision 2831D, and the Hewlett-Packard 34401A. This is in no way meant to be neither an exhaustive review of these meters nor an endorsement of these particular brands or models. I only wish to present the ammeter function on different meters so you can see how the function, leads, range, and placement checklist is employed and interpret the manner in which results are displayed. Given the DMM is the device which you will most frequently employ, it is of paramount importance that you become intimately familiar with your DMM and learn its ins and outs, ranges and limitations and peculiarities. Spend some time with it and get to know your DMM. By all means, RTFM. Read the fine manual. If we recall correctly, 2 major characters in the basic electrical quantities lecture available at the Big Bad Tech channel were voltage and current. Voltage and current don't mean the same thing, and they are not measured in the same manner. In my experience, individuals struggle to understand the concept of voltage, a differential between 2 points. Yet in practice, find it very easy to measure using a voltmeter. The opposite can be said about current. The concept of current, the physical movement of a quantity of moving electrons passing by a point in a given amount of time, is very easy to understand. Yet in practice, very difficult to measure. You can't have it all. The concept of voltage is hard to understand, but easy to measure. The concept of current is easy to understand, but hard to measure. The difficulty in measuring current stems from the fact that you must modify your circuit to incorporate an ammeter into the current carrying path, as we'll see in a moment. Since we're dealing with ammeters this lecture, let's refresh our concept current, where current is the movement of a certain quantity of physical objects, electrons, past a certain point in a given time period. Electrons are packaged into units of coulombs, where a coulomb is a lot of electrons. Therefore, the derived unit of current, the amp, is actually 1 coulomb per second. Therefore, a movement of 2 coulombs in 1 second is a current of 2 amperes, and the movement of half a coulomb in 200 milliseconds is 2.5 amps of current, and the movement of 15 coulombs over a period of 5 seconds is 3 amps of current. Current is analogous to flow rate in hydraulic systems, where flow rate is similarly the quantity of fluid in either liters or gallons passing a certain point in a certain time period, either minutes or seconds. Example flow rates might include a gallon per minute or a liter per minute. The concept of current is pretty easy to understand because it's the physical movement of a physical particle past a certain point measured over a certain period of time. The current induced in a path is directly proportional to voltage and inversely proportional to the resistance of the path. It should be obvious I'm referring to Ohm's law, an incredibly important cause-effect and opposition relationship essential to your understanding of basic electrical phenomenon. The difficulty in obtaining valid current measurements stems from the conceptual differences between it and our previously discussed properties of voltage and resistance. Recall, voltage is a two-point measurement, measured across something, where one point is measured with reference to another. Similarly, resistance is a two-point measurement between the terminals of interest. Current is something totally different and cannot, nay must not be measured across something, but rather through something. Out of my power supply, into my ammeter, out of my ammeter, into my load resistor, out of my load resistor, into my source. Ammeters are placed in series with electrical loads, not in parallel. Old habits die hard, and you simply must break yourself of the reflexive desire to employ an ammeter across something. Ammeters measure current through something. If it seems like I'm making an unusually big deal about the simple difference between across and through, I am, for very valid reasons. An ammeter incorrectly employed in a circuit may damage your circuit, your meter, or you. The difference between careful and correct application of the function, leads, range, and placement checklist when it comes to ammeters may save your life or property. An ammeter has an indoor and an outdoor. The indoor is typically indicated by a red plug and the outdoor by a black plug. You can plug a red lead in a black hole and you can wear a hat on your foot, but that's not its intended purpose. If my simple circuit consisted of a DC power supply and a single resistor, you need to modify the circuit to incorporate an ammeter. You can't just touch points around the edges anymore if you want to measure current through something. The ammeter has to go inside your circuit and be placed in series with the power supply and the single resistor. It should be readily apparent that good safety practices dictate you turn off your power supply while making such modifications. Turn off your power supply, insert the ammeter in series by modifying your circuit, and then turn the power supply back on. This is a major problem for semi-permanent installations that are difficult to change. We'll circumvent this modification necessity when I introduce a special purpose meter called a clamping ammeter or a clamp meter in later lectures. For now, let's stick to traditional ammeters inserted in line with our device of interest. Take your time and think about placement before rushing into current measurements. I've found that students do better if they draw a picture and explain it to their benevolent, all-powerful lab instructor what they intend to do prior to making their first current measurements. Walk yourself through the circuit node by node, device by device. It may sound stupid and you may look crazy, but verbally talk yourself through the circuit and verify each connection is as your picture and description intends it to be connected. Out of the power supply into the ammeter and the ammeter only. Out of the ammeter and into the resistor and the resistor only. Out of the resistor and back into the power supply. At no point is there ever a diversion or choice of paths. The ammeter is in series with the device through which we intend to measure current. An ammeter incorrectly employed in a circuit might have the indoor connected to the outdoor, or worse yet, be across a component. Ammeters don't measure current across something. They measure current through something. You will break yourself of this habit or you will be broken. Voltage is across, current is through. The ammeter correctly inserted in series with the device of interest displays a current value in amps, and the sign of this current value indicates direction. Again, I'm framing this entire lecture series around conventional current, where conventional current is assumed to travel from the positive lead of a voltage source to the negative lead. Electron flow theory, the actual direction of moving electrons, is opposite of this, but the accepted convention since 1752 is positive to negative. who am I to argue against such established precedent? Some people, textbooks, and organizations do choose to go against this generally accepted convention. I'm not saying they're wrong because electrons really do flow negative to positive, but no one does this because the accepted convention of current travel is positive to negative, and every ammeter built since 1752 reads current in this manner. If this ammeter reads 2 amps, it means 2 coulombs per second of conventional current are entering the indoor and leaving the outdoor. I would additionally know that conventional current is inducing a voltage drop in the following direction, positive to negative for this resistor. If I accidentally swapped my indoor with my outdoor, the ammeter would read negative 2 amps. It still means that there are 2 coulombs per second going through it, only they're going in the outdoor and out the indoor. Not only does the ammeter tell me the magnitude of conventional current, it tells me the direction of conventional current via the use of the indoor and the outdoor and the negative sign. I can use the direction indicated by the ammeter to tell if the polarity of a voltage drop is oriented one way or another, or I can use the direction to tell if a battery is charging or drawing conventional current or discharging and supplying conventional current. Look at these incorrect placements of the ammeter. It would not make sense if both the indoor and the outdoor were placed at the same point, nor would it make sense if the ammeter was across our device of interest. In our first incorrect case, current is not going through our ammeter. It's being bypassed. In our second incorrect case, current is going through our ammeter, but it's not going through our device. We'll discuss instrument loading effects in later lectures, but for now, realize an ammeter can be modeled as an extremely low resistance. If our device was the only thing that was keeping current to a reasonable value via Ohm's law, current is not being controlled anymore when an ammeter is placed in parallel, and current can spike to extremely high magnitudes, limited to only by what the power supply is capable of delivering. It is for this reason I am so emphatically urging you to stop, slow down, and think about current measurements. Turn the power off before you modify your circuit. Take your time and draw a picture. Modify your circuit to incorporate the ammeter using the function, leads, range, and placement checklist. Talk yourself node by node through the picture and your circuit and make sure they correspond 1-to-1. Only then do you turn on the power supply to obtain a valid current reading. The takeaway point from this whole preamble on ammeters is that current measurements are through something. Yes, there is an indoor and an outdoor, but the ammeter itself represents a single point measurement inside our circuit through which all of our current of interest must flow. Now that we've had a pretty thorough conceptual discussion of ammeters, let's put some theory to practice and employ our representative DMMs in ammeter mode. We'll use the previously discussed function, leads, range, and placement checklist for 3 different DMMs in ammeter mode to measure the current induced by the fixed 5-volt DC output of the power supply for single resistor circuits. This checklist has 4 steps: function, leads, range, and placement. Follow them in order, and you'll get it right every single time. Skip a step, do a step wrong, or do a step out of order, and you'll get it wrong every single time. First up is our Fluke 87. We'll use a 5-volt DC power supply, supplying our resistor with the following 4-band color code: yellow, purple, brown, gold. In this case, this is a 470 ohm resistor. What is the current you'd expect to observe for a 5-volt drop across a 470 ohm resistor? Ohm's law states that current is equal to voltage divided by resistance. 5 volts divided by 470 ohms yields approximately 10.6 milliamperes of current. Let's use the Fluke 87 and the function, leads, range, and placement checklist to measure and display the current for this circuit. Function. We'll place the Fluke 87 in the DC ammeter mode by turning the mode selector to the milliampere/ampere mode, which obviously stands for amps. Sometimes the ammeter function of a DMM is indicated with either an I or an A, so be aware of this. The Fluke 87 also has a microampere mode next to the milliampere/ampere mode if it is your intention to measure extremely small values of expected current. For both the milliampere/ampere mode and the microampere mode, there are two different flavors of current: DC versus AC. DC is the straight line, AC is the squiggly line. The Fluke 87 defaults to DC ammeter mode and indicates so by placing the letters DC in the display. If you wanted to measure AC current, you'd have to press the blue shift key to toggle between the DC and AC modes. We want DC, so just leave it at DC. Leads. Now that the DC ammeter function is set up, figure out where the leads go. Black lead into the black common hole. This is the lead that will be used as our outdoor for conventional current. Red lead into the red hole indicated with an A, the shorthand for units of amps over it. This is our indoor for conventional current. Notice there's a second input for milliampere/microampere right next door. We'll return to this in a moment. Notice the DMM in ammeter mode is using different lead placement than our previous discussion of voltmeters and ammeters. This is because current is measured through something and not across. An entirely different aspect of this meter is now being employed. If you accidentally had your leads in the ammeter in and outdoor and placed it in voltmeter mode, you'd be in for a world of hurt if you tried to measure voltage, because in effect, you're placing a low resistance ammeter path in parallel with whatever you're attempting to measure the voltage of. This is obviously not the correct location for a low resistance, nor an ammeter, if you want to keep current to a reasonable value. The Fluke 87, however, is kind enough to indicate this is incorrect and beeps at you. The beeps are reminding you to use the function, leads, range, and placement checklist and quit being such a hard-headed dunderpate. Other DMMs don't do this, and you might damage equipment or yourself if your leads are in the wrong place. Range. The Fluke 87 is auto-ranging, so we don't need to worry about manually ranging it. Isn't that convenient? You can force it out of auto range if you want to, but we'll keep it as is. Placement. Now, all we got to do is place our ammeter inside our circuit. Turn the power supply off first. Draw a picture. Where does the ammeter go? Start at any point in your circuit and go in any direction you wish. Let's start at the positive lead of our source and travel clockwise. Out of the power supply into our ammeter indoor. Out of our ammeter outdoor and into one lead of the resistor, out of our resistor and back to the negative lead of our power source. Now, just build the circuit to correctly incorporate the ammeter. Out of the power supply into our ammeter indoor, out of the ammeter outdoor and into one lead of the resistor, out of the resistor and back to the negative lead of our voltage source. Notice there is only a single path going through both our ammeter and our element of interest. Turn the power supply back on. The ammeter is toggling back and forth between 10 and 11 milliamperes of conventional current, close to our anticipated value of 10.6 milliamperes of current, traveling in the direction we anticipated. Recall from the power supplies lecture, available at the Big Bad Tech channel, the function of the needle meters. Notice the meters are not showing the voltage nor current output of the fixed 5-volt terminals because they display the outputs of the adjustable A and B supplies only. Don't get tricked by this. Now let's consider alternate arrangements of our ammeter. If we accidentally swapped our indoor with our outdoor, we observe negative 11 milliamperes of conventional current. The magnitude is the same. The negative sign just means that the amount of current is going in the outdoor and out the indoor for our current orientation. Additionally, consider alternate placements of the ammeter. What if I place the ammeter here? Would it still measure the same current? The answer is yes. Look at the circuit. Any conventional current that originates from the positive terminal of our supply has to travel through the device and then through the ammeter. There is no other path. In this case, the ammeter would still read the same current value and the same direction of travel. Let's build this circuit and verify this fact. We've already got the picture, so all we got to do is build the circuit. Turn the power supply off. Out of the power supply positive lead into one lead of the resistor, out of the other lead of the resistor into our ammeter indoor, out of the ammeter outdoor and into our power supply negative. Turn the power supply back on. The ammeter indicates the same magnitude of current traveling in the same direction. Current measurements in a series path can be taken at any point in a series path because current in a single path with no other alternate means of travel is the same. We'll return to a more thorough analysis of this incredibly powerful and usable observation when we discuss series circuit properties in later lectures. What about the alternate input for the milliampere/microampere and microampere mode? Notice our observed value of 11 milliamperes isn't especially accurate, nor is it especially detailed. We know 11 milliamperes is close to our expected value of 10.6 milliamperes, and that current is traveling in the right direction. However, if we want a little more accuracy, we need to step down to the milliampere input while still in the milliampere/ampere mode. In this case, it shows we're actually observing 10.75 milliamperes of current. The microampere mode is for especially small current measurements and uses this same lead input. I'll admit this intermixing of function, leads, and range is a little confusing for the Fluke 87, but this is where familiarity with your specific DMM pays major rewards. Next, let's employ the BK Precision DMM as an ammeter. The BK Precision is a benchtop DMM. It must be plugged in and turned on for it to operate. We'll use a 5-volt DC power supply and a resistor with the following 4-band color code: gray, red, brown, gold. In this case, this is an 820 ohm resistor. What is the current you'd expect to observe for a 5-volt drop across an 820 ohm resistor? Ohm's law states that current is equal to voltage divided by resistance. 5 volts divided by 820 ohms is approximately 6.1 milliamperes of current. Let's use the BK Precision and the function, leads, range, and placement checklists to measure and display the current for this circuit. Function. We'll place the BK Precision in the DC ammeter mode by selecting the A with a straight line over it. The numbers on the screen are obviously junk because we're not hooked to anything. Leads. Now that the DC ammeter function is set, figure out where the leads go. Black lead into the black common hole. This is the lead that will be used as our outdoor for conventional current. Red lead into the red hole indicated with an A, the shorthand for units of amps over it. This is our indoor for conventional current. There's a secondary input for large current measurements. Again, notice the DMM and ammeter mode is using different lead placement than our previous discussion of voltmeters and ohm meters. The BK Precision, unlike the Fluke 87, will not tell you that the leads are in the wrong place for a given function and will sit quietly in the passenger seat as you drive your lab off a cliff. Don't get mad at the DMM when you're the one in the driver's seat. Range. The BK Precision is manually arranged. We have a choice of 2, 20, 200, or 2000 milliamperes. What's the best choice for this circuit when we expect 6.1 milliamperes? The answer is 20 milliamperes because the 2 milliampere range won't measure 6.1 milliamperes and the 200 and 2000 milliampere range won't measure 6.1 milliamperes accurately. Placement. Now all I've got to do is place our ammeter inside our circuit. Turn the power supply off. Where does an ammeter go? Draw a picture. Start at any point in your circuit and go in any direction you wish. Let's start at the positive lead of our source and travel clockwise. Out of the power supply, into our ammeter indoor, out of our ammeter outdoor, into 1 lead of the resistor, out of the resistor and back to the negative lead of our voltage source. Now build the circuit to correctly incorporate the ammeter. Out of the power supply into our ammeter indoor, out of the ammeter outdoor into the resistor, out of our resistor and back to the negative lead of our voltage source. Notice there is only a single path going through both our ammeter and our element of interest. Turn the power supply back on. We're observing 6.1 milliamperes of conventional current traveling in the direction we anticipated. If we accidentally place the ammeter incorrectly, for example, allowing our current to bypass it by placing the positive terminal of our power supply, both doors of the ammeter, and one terminal of our resistor all at the same node, we would not observe the anticipated value of current Because we're employing the ammeter incorrectly. The ammeter is shorted out because its input is connected to its output like a dog with a strip of bacon tied to its tail. It doesn't make sense to employ an ammeter in this manner. The results are meaningless. Let's finally employ the HP 34401A DMM as an ammeter. This is also a benchtop meter that must be plugged in and turned on to function. We'll use a 5-volt DC power supply and a resistor with the following 4-band color code: orange, white, brown, gold. In this case, this is a 390 ohm resistor. Ohm's law states that current is equal to voltage divided by resistance. 5 volts divided by 390 ohms yields approximately 12.8 milliamperes. Let's use the HP 34401A and the function, leads, range, and placement checklist to measure and display the current for this circuit. Function. We'll place the DMM in the DC ammeter mode by pressing the light blue shift key. This enables the secondary functions of the DMM written in light blue above the buttons. Ammeter mode is signified by DCI. Leads. Now that the DC ammeter function is set up, figure out where the leads go. Black lead into the black common hole. Uh-oh, none of them are black. In this case, the common is the center hole of the right-hand set. This is the lead that will be used as our outdoor for conventional current. Red lead into the red hole indicated with an I, the conceptual shorthand for current written next to it. Additionally, we can tell this is the current input because there's a 3 ampere current rating on it. This is our indoor for conventional current. Again, notice the DMM in ammeter mode is using different lead placement than our previous discussion of voltmeters and ohm meters. The HP, similar to the BK Precision, and unlike the Fluke 87, will not tell you that the leads are in the wrong place for a given function and will sit quietly in the passenger seat as you drive your lav off the cliff. Don't get mad at the DMM when you're the one in the driver's seat. Range. The HP is an auto-ranging meter, so you don't need to worry about manually ranging it. Isn't that convenient? If you want more work for yourself, you can force it out of auto range, but we're going to keep it as is. Placement. Now all we've got to do is place our ammeter inside our circuit. Turn the power supply off. Draw a picture. Start at any point in your circuit and go in any direction you wish. Let's start at the positive leader of our source and travel clockwise. Out of the power supply, into the ammeter, out of the ammeter, into the resistor, out of the resistor, and back to the power supply. Now build the circuit to correctly incorporate the ammeter. Out of the power supply, into our ammeter, out of our ammeter, into the resistor, out of the resistor, and back to the source. Turn the power supply back on. We're observing close to 12.7 milliamperes of conventional current traveling in the direction we anticipated. Now that we've completed 3 iterations of current measurement using 3 different DMMs in ammeter mode, you'd think we'd be just about ready to wrap up the discussion of ammeters, and ordinarily you'd be correct. But I've saved a special surprise for the end. Let's get totalmente loco and use our ammeter incorrectly and see if we can anticipate and interpret what we're seeing. Again, understanding the content of the DC Power Supplies lecture, available at the Big Bad Tech channel, we realize this power supply is current limited, and the 5-volt power supply is incapable of supplying current in excess of 0.2 amps or 200 milliamperes, even though it says 2 amps on the front. You would never do what I'm about to do in an industrial setting, nor with a supply that is capable of generating current in excess of your ammeter's maximum safe value. A correctly deployed ammeter is placed in series with the device through which current is to be measured. Circuits must be modified to incorporate an ammeter. Let's say, though, you got lazy and decided not to modify your circuit and used an ammeter like a voltmeter, placing it across the terminals of our resistor. With an understanding that an ammeter can be modeled as an extremely low resistance, try to anticipate what would happen and what the ammeter might read, given that the maximum current this supply is capable of delivering is 0.2 amps or 200 milliamperes. Pause the lecture and think about this. Bam, you guessed it, because the parallel combination of a 390 ohm resistor and a low resistance is extremely low. The supply indicates it's an overload and pegging the limit. The ammeter has the least resistance in a parallel combination and carries most of this current. Don't do this. This is dangerous. And the only reason you didn't destroy this ammeter is because the power supply is current limited to 0.2 amps or 200 milliamperes. Additionally, this ammeter has a fused input. I know we haven't discussed circuit protection devices like fuses yet, but realize there's a 3 amp fuse on the ammeter input that simply melts anytime current is in excess of 3 amps and becomes an open circuit. If your power supply is capable of supplying more than 3 amps, a fuse would just melt instead of the internal workings of the ammeter. The fuses used on the HP and the BK Precision are monetarily very cheap. Fuses for meters like the Fluke 87 are not. Fuses in lab environments, however, are at the very end of an extremely long session in the iron chair position. Don't be the person that walks out of lab with extremely toned quads and glutes because you don't know how to use an ammeter. In the event you inherit a rotating workstation in the lab environment used by numerous students, always check to make sure that the ammeter input fuse is in place and the fuse itself isn't damaged. Lab equipment gets hammered by generation after generation of students just learning how to use this stuff, and equipment will sometimes just die of despair and exhaustion. If the lab group in front of you accidentally shorted the ammeter and blew the fuse, the ammeter won't function regardless of its correct placement. The blown fuse is now an open in your circuit. Without a complete path, no current will flow, nor will any voltage drop be observed across the resistor, even if the power supply is on. Sometimes it's not your circuit. Sometimes it's not your lab partner. Sometimes it's faulted instrumentation that is inducing an error. Here's a picture of a DMM in ammeter mode with the input fuse removed. Ordinarily, a 5-volt source supplying current to a 390 ohm resistor would induce 12.8 milliamperes of current, but we're observing nonsense, even when the ammeter is correctly placed. When a functional fuse is reinserted, we're observing close to our anticipated value of 12.8 milliamperes. All right, that about wraps it up for this quick look at the ammeter function of our representative DMMs. Don't think we're done with ammeters though. This and all the other functions of the DMM will be routinely employed in later experimental verification lectures, circuit analysis, and troubleshooting scenarios. We've got 3 balls in the air now, and we need to juggle the ohm meter, the voltmeter, and the ammeter without dropping them. Remember to read the fine manual about your specific DMM used in ammeter mode, and always, always, always use the function, leads, range, and placement checklist every time you employ it. Current goes through something, and circuits must be modified to incorporate an ammeter in series with the element of interest. In conclusion, this lecture took a brief look at the ammeter function of the digital multimeter. We use the function, leads, range, and placement checklists for different DMMs in ammeter mode and discuss conventional current direction. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.